Welcome to our fourth week of class. The plan for today is to start with section 3, which is electrostatics in the presence of matter. Like I said, welcome to our beginning of section number 3. This section is going to be, actually most of it, if not all, it's going to be new stuff. It's for the first time we are going to put matter in the equation. And by matter, I do not mean conductors. We already know a lot about conductors, where there is an unlimited supply of charge, which is mobile, and therefore they are, from the electric point of view, conductors are relatively boring, meaning they always shield the field and, their properties are the ones they are. But then this section, we're going to talk about insulators, about dielectrics. And the physical properties of dielectrics are a lot more intriguing. So most of it, if not all, of the stuff we're going to see is actually new. So for that, I think for the first time we enter the part of our syllabus that actually should be a little bit more interesting. Okay, so you already have the slides in the virtual campus. So this is what we are going to work on for the next 3 weeks. All right, the quantification of electrostatic fields in matter. And just like we did in electrostatics in vacuum, in the absence of matter, other than conductors, which are, like I said, really uninteresting from the electric point of view, here for the first time we're going to have a lot of new concepts that you need to master. Okay, so the next 3 weeks we're going to work like this. First, this very week, Tuesday, today's Tuesday, Wednesday, and Thursday, we're going to work on defining what is the concept of electric polarization and polarization bound charges. The idea is that in dielectrics, when you apply an electric field, the material cannot shield the external field like a conductor would because there is no mobile charge. So other things happen, right? So this is the point about these first couple of points. What things happen, how to quantify them. And then we will talk by the end of the week about the concept of a new vector. This one you probably do not know from last year, which is the electric displacement vector, which is a sort of electric field, but we'll see this is not really an electric field, which only depends on free charge, not on polarization or bound charges. So anyhow, it's a new concept, right? This will be this week. And then on Thursday, we'll probably have material by then to actually work on a couple of practical examples. And then we'll also solve the homework that you have to turn in by tomorrow, the one about the electric dipole, right, that you are actually working on right now. A lot of you have already done it very well, by the way. This was an exam. I already said this, a problem in an exam last September. So if you can do this, then you pass the subject, right? Anyhow, this is this week. Now, next week, we will go over this concept a bit more, talk about the constitutive relations, which are the relations that hold between the electric field E, the polarization P, and this electric displacement new field D. Talk about boundary conditions when you have surfaces in between two different materials. So far, the only surface we have studied is the surface between a conductor and vacuum. Now we're going to put two materials in the equation, see what happens at the very boundary, right? And we'll also work on problems. There's always been a problem on this section in the exams of this subject for as long as I remember. For as long as I remember means the years that I've been a teacher of this subject and also the years when I was studying, right? So this is always, because this section basically contains the previous sections. So please make sure you do not, disconnect right now from the subject. And keep working for the next 3 weeks on this, because this means you would have already half of the exam done. Okay, anyhow. And then the last week we'll talk about the electrostatic energy and a lot more problems. That will be the plan for the next 3 weeks, more or less, approximate. Anyhow, so today we're going to talk about electric polarization. What is this? Well, like I said, dielectrics basically are insulators. We are going to use both, let's say, terms indistinctly, right? The dielectrics or insulators to us is going to be the same, going to mean the same sort of material, a material where there is no free charge. By free charge means loosely bound charge, like in the metal, like those electrons in the conduction, in the conduction C, the conduction, let's say, the electron-free, let's say, glue, right, that can move freely. No, we don't have that here. Here we have materials that are constituted by other types of atomic bonds. For example, ionic bonds. In an ionic bond, you know that you have let's say, for example, in sodium chloride, you have a chlorine that has 7 electrons in the last level and a sodium that has 1 electron in the last level. Sodium is so looking forward to losing this 1 electron, and chlorine is so looking forward to sucking it, right? So there is a transfer of 1 electron from sodium to chlorine, and now sodium becomes a cation and chlorine becomes an anion, and therefore they actually just attract each other because of pure electrostatic forces, right? And this is how the material is basically constituted, as you know since whatever school. Now, the thing is, in such a bond, there is no free charge whatsoever. All electrons are like tightly bound into their orbitals. What happens when I put this material into an electric field? An external field. We'll see about that. Okay, so, but this is the point about all dielectrics. All charges are localized, heavily localized. They are attached to their respective atoms or molecules because of the type of bond. Atomic bond. Atomic bond at the very, very end is at the very basis of any possible property of a solid that you can think of, okay? So this is the important thing to have into account as opposed to conductors where we had an unlimited supply of mobile charge. No, we don't have that here anymore. So when we have dielectrics or insulators, which are typically ionic compounds or some covalent compounds, in covalent bonds, you know also that the electrons are sort of localized into this covalent bond that is shared between 2 neighboring atoms. One way or the other, when we apply an external bias, a voltage, or an external field, if you want to call it like that, charge within the atoms will sort of move under the force, the electrostatic force resulting from the external field, but not too far. They can only move within their atoms. They cannot go away and go to the surface and shield the field or anything like that, okay? So at best, charges in dielectrics move within their molecules or atoms, where they are in the first place. So some microscopic arrangements of charge can occur, but they are nowhere near as dramatic as in conductors, okay? And the properties of dielectrics, therefore, are going to be very, very, very different. However, even if this affects this charge movement within the atoms, these movements are super tiny, these micro arrangements only take place within a given atom, which has a really, really small size. Remember, 10 to the minus 10 meters at best, like the scale of 1 Armstrong, a tenth of a nanometer, if you want to look at it like that. It's happening in all of the atoms of the system simultaneously, and this is we're talking of a lot of particles, right? The number of Avogadro is 6 times 10 to the 23 atoms or more. So macroscopically, all of these tiny rearrangements might actually add up and result in a macroscopically noticeable response. So dielectrics actually, when you apply a field on them, things happen and you see them from the outside, even if they're actual rearrangements of charge are very, very, very tiny. Okay. So let's just look super fast at precisely those the mechanisms, those intrinsically small mechanisms taking place within the atoms or molecules. When I have a dielectric, right, an insulator, and I apply an external field, there are 2 main mechanisms for the material to respond to the field. Okay, charge gets distorted within the atoms or molecules that are constituting my system. It doesn't move away, but within this unit, think of atoms as like the Legos, the pieces that constitute our materials. There are 2 mechanisms that take place when an external field is applied to these atoms. One of them is stretching of the atoms, and the second one is rotation of the atoms if they have a finite dipolar moment to start with, like molecules, like some molecules, for example, water. We'll see about that, but let's look first into what happens to atoms or non-polar molecules under an external field. Let's assume we have a material made of atoms, like this one in the sketch right there, where of course we have the positive charge in the nucleus, these protons, and then we have these electrons in their clouds, in their orbitals around the nucleus, and in principle the atom is unpolarized. What happens when my material made of all these unpolarized neutral atoms, let's say, or even if they are ions, but they have some sort of symmetric configuration, okay? What happens if I apply an external field? there's going to appear some force, an electrostatic force on the negative and positive charge particles in every atom. Under the action of an external field generated by some external charge that I put somewhere, okay, I don't care right now about the causes of the external bias, the nucleus and electrons actually feel forces that go in opposite directions because the force is going to be Q times the electric field. Obviously, electrons are negative, so the force goes like minus Q E, and then the nuclei, the protons are positive, so the force is the appearance on them actually goes like positive times QE. In other words, in the direction of the external field. So the atom becomes polarized. If I put some external charge in the presence of my atom, like some negative and positive charge, so therefore the field goes from positive to negative, externally, the atom sort of loses its symmetry, and the centers of gravity of positive and negative charges just get away from each other slightly. These displacements are super, super, super tiny. I'm talking like 10 to the minus 10 meters. That will be the length scale, right? Even less than that, but they happen, right? So the atom becomes polarized, okay? When the electric force and internal reactive forces reach equilibrium, what basically happens is that the atom has lost its symmetry when it regards to the centers of mass of positive and negative charge. Then, if I actually look at the atom from a little bit more farther away, it looks like this sketch we have here. We have our external negative and positive charges, which generate some external bias, and the atom has become a dipole. Somewhat. This separation of centers of gravity of positive and negative charge actually looks from the outside like a super tiny dipole. We say that the atom has become polarized and a small dipole moment will appear, which obviously goes from the negative to the positive centers of mass within the atom. Okay, this dipole again can be quantified, and actually this value is basically Q times D, where D is the distance, the separation between the positive and negative charges, right? And we can also say for most materials and under the presence of external fields which are not absurdly large, that this induced dipole is going to be linear with the external field. In other words, since the separation of positive and negative centers of mass depends on the force, which is linear with the field, right? One would think that twice the external field, twice the induced dipole. This is what this equation means. So there is some constant, and which charge should we put in the equation? Very good question, Pedro. There is not an obvious answer to that, and we are going to see in a moment how much charge you have to put into the equation. Right now, let's leave that open. Okay, because it's going to depend on the atom, on how many electrons it has, if it's a large atom with lots of electrons outside. I mean, not all of the atoms respond in the very same way. And as a matter of fact, I'm glad that Pedro was asking this question, because this constant, we'll see in a couple of sections, that is not necessarily a constant. It can actually be a matrix, because atoms do not get polarized with the same strength along all the possible directions. For example, think of an atom that has lots of d electrons. You know, the d orbitals can be quite asymmetric. So this or even p orbitals, they look like 8s, right? So there are some directions of space that are preferred for the electrons to be, and then it can be this in principle a linear relationship can be quite complicated. We're going to talk about this for the whole section, right? So let's leave that open, Pedro, for the time being. But the fact so far is that for most materials under small fields, we will sort of assume that the response of the material is linear with the applied field. Twice the field, twice the response, twice the separation, twice the whatever, okay? We are going to, in principle, define this constant, as what's called the atomic polarizability. Its value is going to depend on the atomic structure, like I said, because it's not the same if we have F electrons out there or we only have like S electrons, like one hydrogen atom, right? And for atoms, especially if they are not very heavy atoms with high atomic numbers, it can be a scalar, but in molecules in general, it ends up being a matrix and a tension. So it's not necessarily an easy question for complex materials, but we'll see examples of this. In principle, we'll just define it, and let's just think of this parameter as the parameter that actually takes into or somehow resumes the response of my material to the electric field. Again, these are quantities that at the end of the day people measure in labs, so they tend to be experimental quantities, but we'll talk about them a little bit more. But in principle, that would be the first mechanism, independently of quantification right now. Let's just think of this, is just understand the mechanism, okay, of lots of materials, the ones made by non-polar, constituted by non-polar atoms or molecules, okay? You just put an external field and the atoms become polarized, and there are induced dipoles. And these dipoles are, the larger the external field, the larger the dipole, in principle, okay? That's the first mechanism that the dielectric can use. Most dielectrics use actually to respond to external fields, stretching. So the atoms become stretched and dipoles are induced. Now, the second mechanism only happens in polar matter. You know that there are some materials, and by materials I mean substances in general, because we can also talk about liquids. Liquids also have responses, electric responses. So they are also considered sort of condensed matter anyway, that are made by molecules that already have some dipole moment built in them. For example, water. You know that water is made by one oxygen atom and two hydrogen atoms, right? And this bond between the oxygen and the hydrogen takes place via the p orbitals of oxygen. There are two p orbitals of oxygen half empty, and they just bond to one hydrogen atom each. Right? In principle, p orbitals are separated by 90 degrees, but since we have two oxygen atoms, hydrogen positive atoms at the very end of the sticks right there, well, basically they repel each other and the atom, just the bonds become a bit more open. So the actual final angle in the molecule of water between the two bonds is more like 140 degrees, not 90. But what basically happens is that in this molecule, just because the oxygen is a lot more electronegative than hydrogen, as you know, the oxygen sort of sucks the electrons a bit closer to it, even when this bond is basically covalent, right? So the centers of mass of positive and negative charge are not quite in the same place. And as a matter of fact, as you know, the molecule of water has a finite dipole moment that points like along the symmetry plane of the molecule towards the positive hydrogen, okay, ions. What happens if I put a polar material or a polar substance like liquid water, like this one, in the presence of an electric field? Well, like we already studied at the end of last section, if we have a dipole in the presence of an external field, a torque will appear on the dipole. The dipole will rotate and align itself with the external field to minimize its potential energy. So if I not just have one dipole, but I have lots of them, because I have a material, for example, let's think of a flat capacitor, two metallic planes filled with the dielectric, which is polar, for example, filled with water, right? And I actually charge the capacitor, and I put a lot of positive charge up here, a lot of negative charge right there. An electric field appears from positive to negative, and this field will actually force all of these dipoles that in principle were randomly oriented in all possible directions, right, to more or less become aligned with the external field. In this particular case, the material again becomes polarized because there is all of the dipoles are pointing in the same direction, right? It's like in the previous case. Let me go back for a second. When we had all our non-polar atoms, if we have a material made of atoms like this, when I apply an external field, all of the atoms of the material become polarized in the same direction. So lots of tiny dipoles appear and they are all parallel to each other. In the case of polar matter, a similar response appears just by rotation of the already present dipoles. All right, the substance is polar in the first place, but then an external field aligns one way or the other. We say that the material becomes polarized. In this case, there is a rotation mechanism that makes the dipoles in every molecule just rotate to become more or less aligned with the field. Be it by rotation or be it by stretching, just like in the previous slide, under the presence of an external field, dielectric matter will become polarized. If it's made of polar molecules, then it will be because of rotation of the existing dipoles. If it's made of non-polar atoms or molecules, then it will be because of stretching. One way or the other, be it by induced dipoles or by rotating of actually already existing dipoles, the material becomes polarized. And this means that there is an electric response microscopic mechanism that makes things become, let's say, interesting, okay, at the atomic or molecular level, and there is a response that correlates with the external field. So the picture, one way or the other, be it by rotation or by stretching, becomes the same. The microscopic picture of the material arises that lots of tiny dipoles, and by lots we mean numbers of Avogadro, so that's lots with capital letters, okay, lots of tiny dipoles exist, and they are sort of oriented more or less, quite a lot actually, oriented with along the external field. Now, how can we quantify? Can we find a convenient way to write equations that help us quantify this response in general? Well, let's define a very important quantity, okay, in dielectrics, and it's going to call electric polarization. We are going to define the polarization, capital P, as the net dipole moment per unit volume. In other words, if I have a material like this potato here, and it's made of atoms, and let's assume it's polarized. I don't care if it's because of a stretching or because of rotation, but let's just assume that there is lots of tiny dipoles in my material. Okay, so, and I just look at some position within my material, for example, this point right here, R prime, right? And I look at how many atoms and dipoles do I have around my position. So if I just sum all of those tiny dipoles and divide the net value, okay, over the volume of the little cube within which I'm actually accounting for those dipoles, the net dipole moment over the volume will be what I call electric polarization. In other words, it's the dipolar moment per unit volume. It's like a density of dipolar moment. It's the intensive quantity associated with the extensive quantity, which is the dipole moment. All right. So when I actually make this volume go to super the tiny, where it's the limit where it's super tiny, then I will basically assume the polarization, which is a function of R prime right there, not of R, but that's okay. I'll fix that later. Not very important right now. As dP over dV. Okay, it's just the density of dipolar moment, and it's the quantity that can change. It can be higher over here, it can be lower over there. So this is actually why I have to go to the limit where I define things in a super tiny way, just like I did with the charge densities. No big deal, because they can be inhomogeneous. All right. So the polarization, it's a vector field that can be uniform or not. It will depend on how these little dipoles are distributed within my material. I might have a material that does not have a chemical composition that is uniform. For example, maybe I have some alloy, some mixture of two elements that for some reason has not been stirred up very well enough, and I have more density of atoms here than there, and therefore the polarization is not uniform. Or maybe I have a material that has some polarization on the surface but doesn't have it in the interior. We'll see examples of this. But in principle, the polarization is like the charge density. It doesn't have to be uniform. Now, units of polarization obviously are going to be units of dipole moment over units of volume. Dipole is Q times distance. Volume is distance to the cube. Therefore, the units of polarization are charge over this surface. Okay? Coulomb per meter square in the metric system. And we will say that the dielectric, therefore, is polarized if there is this field, the polarization field, well defined, for every location within the material. And if by any chance we have an area where the polarization is zero, then the dielectric is not polarized over there. Okay? So it's just like the charge density, but in this case is the dipole density, the amount of dipole moment per unit volume. Okay, so once we have actually discussed the polarization like that, let's go a bit further and talk about polarization charges, which is a new concept, okay? The question arises right now that if we actually have a polarized dielectric with all these tiny dipoles that we can now quantify, or at least say how many dipoles we have in every location in my material, okay, then if I have a material that is polarized, I don't care why. It's some external field, there is some stretching or rotation, I don't care what is the mechanism, but let's assume we have a dielectric that is polarized. Then we have lots of positive and negative charges all over the material, right? So then there's going to be a field generated by the polarized material. And a field that is independent of, well, it's not quite independent, but I'm talking about the different field that the external field. Obviously, the internal dielectric field plus the external field add up to find the total field in my universe. However, for the time being, let's just think about the question of what is the field generated by a polarized material. In other words, remember, in a conductor, we were talking about the field on the surface that was always normal to the surface, and the value was sigma, the charge density over epsilon naught, and the field inside that was always zero when the equilibrium had been reached. Okay. Now I'm asking the same question, but in a polarized system. What is the field associated with the polarization itself? Okay. Well, let's calculate the field by looking at every tiny dipole. We know how to calculate the field of a dipole. You guys are doing it right now as you solve the homework for previous week, right? So let's look at the field generated by every tiny dipole in my material and then sum all of them for the whole volume of the material, as easy as that. The idea is not complicated. Now, of course, it can be difficult because we'll have to do a number of integrals, but in principle, that's technical issues, right? Which just is not really conceptually difficult. Let's just think of one dipole, P, in some place, R prime. All right, this just have some dipole moment here, like this red tiny dipole associated with some atom that has been polarized. Okay, and let's just pick some coordinate system, and of course then write the coordinates of my dipole as R prime. That will be the source of my field, and then let's calculate the field in some position R, wherever it is, far away, close. I don't care. I'm just going to look for the analytical solution right now. In this particular case, the vector that goes from the source, my P, my dipole moment, all the way out to R is obviously R minus R prime, this green vector right there. Well, we know how to calculate the field of a dipole, don't you? It will be 1 over 4 pi epsilon 0, P, the dipole, dot, scalar product, R minus R prime, the vector that goes from my dipole all the way out to the point where I want to calculate the field, over R minus R prime to the cube. I mean the modulus to the cube. We know this expression. No big deal. Now, let's go a bit further and remember a couple of mathematical expressions that we know from the first section. Remember the divergence of a scalar times a vector, right? Would be scalar times divergence of the vector plus vector dot divergence of the field. This is a scalar. Remember this expression, we have used it in the past. And now let's also remember the following expression. The gradient of 1 over R minus R prime is U R minus R prime, the unit vector in this direction, over R minus R prime squared. And if instead of if it was the gradient with respect to absolute coordinates, R coordinates, X, Y, Z, there will be a minus in front of this. But if I am let's just for a moment think of what happens if I want to calculate the gradient with respect to prime coordinates. What I'm going to do is change the prime coordinates. Now, in other words, move within the volume where my sources are present. Now, since R prime is in here, with a minus in front of it, if I calculate the gradient with respect to prime coordinates, I have to use the chain rule, and at the very end of my derivative, there will be a derivative with respect to minus R prime, that's a minus 1. This derivative kills the minus that would be in front of this expression for absolute coordinates. So the gradient in prime coordinates of 1 over the modulus of R minus R prime is just the unit vector in the R minus R prime direction over the modulus squared. Okay? So if I have those two things into account, then what if I want to calculate the small piece of potential created at the location R by a small dipole located at R prime? And by small dipole, I mean now a dipole that I'm gonna make it go to 0 because it's super tiny, because I'm talking about an atom with a super small stretching. Super tiny. I'm gonna call it differential P. It's a small dipole. In this particular case, if my P is now a small dipole dp, then it will generate a field and a potential and position R that will be also small. So my differential potential, my dV, will be the same thing, but just put a dp in here. Okay, that is the small potential caused by a small dipole at R prime, and we're calculating in R. Now, what happens, how can I rewrite this expression to then add up to imagine I not only have one dipole, but I have a whole volume full of dipoles, like a polarized material. In order to make that extension, let's just rewrite for a moment that according to the definition of polarization, remember my polarization is dp over dv, the amount of dipole moment per unit volume. I can rewrite my differential, my super tiny dipole moment dp as polarization at R prime, the amount of polarization in this volume, times dv, which is the small volume around my point. So if I write this into the integral, if I now want to just calculate the total, let me get back for a moment. Imagine I don't have only one dipole, but a whole potato full of dipoles like I had in the previous slide. And I want to calculate the total potential in some position R. What I have to do is sum the contributions of all tiny dipoles within my potato at R. And that's going to be the sum of all differential potentials extended to V prime. In other words, evaluating the potential generated by every tiny dipole dp at R prime, but just let's change R prime and let make it sweep the whole volume of my sources V prime. So if I do the integral and the sum of all possible small contributions of all possible small dipoles and my position R, then I get the total electrostatic potential at R. Now, inside my integral, what am I going to write? The expression that I had in the previous slide. Small dipole times R minus R prime over the modulus to the cube, and this I have to integrate over the whole volume V prime. In other words, I will insist R prime sweeps every possible location within V prime. Okay? Now, I will rewrite my dp as P dV, like I wrote in the very last line of the previous slide. All right. And now I will use the expression that I had here. Let me go back just to remember right there. The divergence of a scalar times a vector can be rewritten this way. But what do I have inside my integral? I have P times dV, that's a vector, dot R minus R prime over its modulus squared. And this is exactly, this quotient is exactly right there. U, the unit vector in the R minus R prime direction over the modulus of R minus R prime squared. In other words, that is exactly the gradient of 1 over R minus R prime. What I have into this integral is a factor that looks like this. A vector times the gradient of something. So what I'm going to do is take this term, A scalar times divergence of my vector, to the first term of the equation as a minus, and rewrite this thing, which is again vector times the gradient of something, as, here it is, vector times the gradient of something, right? So as what? As the divergence of one thing times the other, vector times the scalar, and the scalar now is going to be 1 over the modulus of R minus R prime minus 1 over R minus R prime scalar times the divergence of the vector, in this case, the divergence of P. All right? It looks a lot of integrals, it looks a lot of math, but do it yourselves is not difficult to understand. So what I've come to the moment, to the time where I have my potential written as a sum of two factors, two terms. This one, which is the divergence of something, plus another one, which is just a scalar, because here we have the divergence of a vector, that's a scalar, over a scalar, that's a scalar. I will use my Gauss theorem to rewrite this term, which is the integral of a divergence of a vector, as the flux of that vector across the surface that defines my volume V prime. And that will be the integral over S prime, the surface that defines my volume V prime, of the flux of this vector, which will be P dot ds prime. Okay, so this term comes from here using the Gauss law. And the other one, I'll keep it the same one, just I'm going to put the minus inside the integral, no big deal, it's the same term. And let's look very carefully at what I have right now. I have that the potential is the sum of a surface integral of a quantity that happens to be a scalar, because P times ds using a dot product is a scalar, right? Modulus of the first one, modulus of the second one, cosine of the relative angle, plus another term here, which also is a scalar, because the divergence of a vector field is a scalar. It has a minus in front, who cares? So at least I have come to the realization that I have the expression for the potential, the total potential at the point R, due to the presence of a polarized dielectric with a polarization P, right? Which is a function, it can be homogeneous within the dielectric or it can be homogeneous. At this point, we have not made any assumption in this respect. But it's the sum of two things that at least they happen to be scalars. Good. This is good news. Let's look at those two terms simultaneously, okay? For a moment. And again, just keep in mind that what's in here is the polarization of my dielectric that has been generated by an external field, which I'm not really caring about right now. Just the fact we have a polarization generated by an external field in a dielectric. I don't care about it. I'm just calculating the potential associated with the field in the dielectric. Again, let's forget about superposition with the external field for now. Just the field in the dielectric. Well, these two things, these two contributions actually look like a surface contribution and a volume contribution. And this is very interesting right now, because if we look at those two, the first term actually looks like the following. 1 over 4 pi epsilon naught, well, actually the constants are in both terms, which is good because, you know, potentials for charge densities have this factor in front of them, of a surface integral of 1 over the distance, and here I have something times differential surface. And here I have 1 over the distance, and here I have something differential volume. If I define, for the time being, the following quantity that looks a lot like a surface charge density, where this sigma surface charge density associated with polarization, let's call it sigma p, as p, the polarization, delivery point, dot the normal vector. Remember, my ds normal vector is the normal vector un times ds, just the modulus of ds, okay? If I rewrite this term using this definition, and I also call what's in here in the volume integral this minus the polarization, the divergence of the polarization in prime coordinates as a charge density, then this potential can be rewritten as the contribution of a surface charge density calculated over the whole surface of my material, plus a contribution of a volume charge density calculated over the volume of my whole material. And again, this is my differential Q in 3 dimensions, rho dV, and this is a differential Q in 2 dimensions, sigma ds. The only thing I've done is actually rewrite things just that my sigma p would be p times un, and my rho p would be minus the divergence of p. In other words, if I think that that quantity in here is like a surface change density, and that this one behaves like a volume charge density, then I can just rewrite the electrostatic potential resulting from the presence of a polarized dielectric as a surface contribution of some surface charge density plus the volume contribution of some volume charge density. Being those charge densities, the surface and the volume, defined like this in terms of the local polarization. So I've actually so far found a mathematical trick to rewrite, let's say, my potential here the sum of all dipolar potentials resulting from the superposition of the potential of every tiny dipole within my material at some place R, right, as the superposition of two contributions. A surface contribution that has units of potential plus a volume contribution that also has units of potential. Okay? The only trick so far that I've played is just redefining the divergence of P as minus a charge density, a volume charge density, and the normal component of P on the surface as a surface charge density. If I believe that those two are charge densities, then I have rewritten the potential of my dielectric as just a potential resulting from a surface and a charge density. Well, we are going to define and actually call those two charge densities that I just defined, let's say mathematically, as what we're going to call polarization charges. And they are bound polarization charges because they are associated with localized charge. The volume polarization charges rho are going to be the minus the divergence of my polarization, and the surface charge density, the surface polarization charge density is going to be the normal component on the polarization on the surface. Okay? And even when this trick that we have played is basically a mathematical trick to get to this way of writing the potential, these charge densities actually are real, and they really reflect the amount of polarization charge present in my system, right? They really correspond to the charge that appears on the surface of the dielectric because of the induced polarization processes, and we're going to see examples of this, along with the distribution of polarization charge inside my material. In other words, these are actual charge densities associated with the mechanism underlying the polarization itself in the dielectric. So if we know the amount of local charge density, the dipole density moment, in other words, polarization, then we can calculate the divergence of P and the normal component of P on the surfaces and substitute or replace my dielectric by two contributions. The contribution of the surface polarization charge plus the contribution of the volume polarization charge. To what? To the potential. And calculate just like if they were normal, let's say, just regular charge densities like the ones we have used in the previous section. Okay, so we can replace the dielectric itself by two densities of charge and calculate the potential associated with those, and therefore then we can calculate the field as the gradient of the potential, the inverse. So it's actually a quite useful mathematical trick. And by the way, since the polarization charges, I'm saying, bear with me for now, and we'll see examples so you get to the realization that I'm not lying to you, right? Since they are actually real and they are the charges associated with this polarization process that Pedro was asking before, how much charge do I have in the dipole? These are the charges that we care about. It depends on the polarization itself, the process, right? Since these polarization charges are the result of inducing a dipole in the first place in an atom that is neutral, the total polarization charge in the material must be zero. Because if I have a neutral atom that becomes stretched and therefore the local moment is induced, the total charge of the atom is still zero. Okay, the centers of mass of positive and negative charge have slightly moved apart from each other. Fine, but if you add the total charge, still the number of electrons and protons has to be the same, so totally zero. In other words, the total polarization charge in a system must be zero, and that would be the sum of the volume polarization charges plus the surface polarization charges. However, the volume polarization charge is minus the divergence of P. Let's put that in here, right here. And the surface polarization charge is actually the flux of what? Of P. P times the unit vector, in other words, P times ds. So sigma P is P times UN, but UN times ds is ds vector. However, what do we have here? The flux of P across surface S prime. What volume is inside V prime? I mean, inside S prime, V prime. So what does the Gauss theorem say? That the flux of a given vector field across the surface that defines a volume is equal to the integral of the divergence of P along that volume. Well, if we have a minus here and this term is identically equal to that one, then obviously this has to be identically zero, right? So we are going to work on problems where we calculate polarization charges, and quite often we'll say, hey, make sure that the charge neutrality holds for our system. Well, what you'll have to do is calculate this integral for the volume polarization charge that you get along with that one, right? And just make sure that they match. Okay, and if you go over our list of problems, and then also over exams, previous years, there are so many times that we actually ask this question in the exam. Just make sure that the polarization charges that the neutrality condition holds and the total polarization charge is zero. It must be zero physically. Okay, well, you have to discalculate this integral and make sure you get a zero. In other words, that there is no extra charge having to go into the system for polarization to happen. It's just a local mechanism associated with either rotation of dipoles or inducing dipoles that just happens in neutral systems. You don't need more charge. But even with when you have this, let's say, macroscopically neutral systems under the action of an external field, there can be a polarization in them. Okay, so that is the macroscopic thing about dielectrics, right? And then the potential is therefore equivalent to the potential produced by the superposition of both a volume charge density in 3 dimensions and a surface charge density in 2 dimensions. So now, instead of actually integrating the contributions of all of the infinitesimally small dipoles that we have in our system and having to look at the dipole of every atom and calculate the contribution of this atom to the potential in this place, and then sum for all the possible atoms, which is an sometimes difficult integral, what we can do is, if we know the polarization field, just calculate its divergence and the normal component and just integrate the potential as if we had a surface contribution and a volume contribution, and those are our polarization charges and their fields. Okay, and then of course, when we know the potential, then we can find the electrostatic field generated by the dielectric that has been polarized as minus the gradient of B, which is not a difficult thing because it's just a derivative. We always know how to calculate derivatives. Okay, examples. Let's, for example, have a problem where we have a uniformly polarized sphere of total radius capital R. So they tell us that the polarization field happens to be known and it's uniform and it has a value of 2 times 10 to the minus 6 coulomb per meter, square, and it's parallel to the z-axis, right? Just like we have plotted in here. It's a sphere, and then there is a polarization that is homogeneous within the whole sphere. In other words, we have a density of dipoles that is homogeneous and uniform and constant and everything over the sphere. And they say, first, find the polarization charges, the bound polarization charges, and then also imagine you want to find the potential in the middle of the sphere at r equals 0. Okay? We could find the potential everywhere in some position R. By the way, R can be inside or outside the dielectric. We haven't made any distinction about that. Okay, but in particular, they want us to know at the origin. Okay. By the way, before even calculating anything, one would like to know: can we think in advance what is the response to both parts of the question? For example, the bound polarization charges. Well, a uniform polarization, like we have in this problem, means that we have a uniform density of dipoles all over my sphere, and they are all the same. In other words, if my polarization points upwards, this means that we have lots of tiny dipoles which are vertically oriented and the plus contribution is at the north and the south contribution is at the south, right? Or let's say up or down if you want to, according to the x-axis. But since it's a sphere, we can talk about north or south if you want to. And then this means we must have lots of positive charge on the top half of the sphere and lots of negative charge on the bottom half surface of the sphere. And in the middle, since our polarization is uniform and the density of dipoles therefore is uniform, what this means is that we have lots of dipoles, like we have a, let's say a picture. Let me go back real fast for a moment. Can it be studied as a big dipole? Yes, of course, Alejandro, that's going to be the conclusion. Yes, it can. But let's not anticipate. Let's imagine we have a material that has lots of dipoles like this one, and they are ordered. And the density is homogeneous, and they are regularly arranged, right? So in principle, on the bottom surface here, we will have a density of positive charge. In the upper surface, we will have a density of negative charge. And in between, if we actually look very, very close and we have a density of dipoles which is homogeneous, we're going to have positive and negative charge homogeneously distributed very close to each other. This means that as long as I am averaging the charge density over distances that are bigger than 1 atomic radius, I'm going to see, let's say, an average of 0 net charge in the middle, because there is positive and negative charge very close to each other. So in principle, just thinking intuitively, okay, about the problem, when they ask what kind of polarization bound charges I am going to find in a body like this one, in particular a sphere that is homogeneously polarized, but it can also happen if it's not a sphere. Anybody that is homogeneously polarized, I have to get something that looks like a lot of positive surface charge on the top, a lot of negative surface charge in the bottom, because the polarization points upwards and so do the dipoles, and very likely no charge in the middle, as long as I'm looking things with a magnifying glass that is bigger, I mean magnification is larger than 1/2 of an atom, which is not difficult. Actually, it's difficult to look at things with polarization, with magnifying glasses that allow me to see things within the atom. That's very difficult, but anyway. So without even making any calculation, we can come to the realization of a result, and is that in every possible body, be it a sphere, I have not made any assumption in this intuitive, let's say, reasoning about the shape, okay? In any body that has an homogeneous polarization, very likely I am not going to have polarization charges in the middle. This means bulk, three-dimensional raw, right? Charge density in 3D, it's going to be 0. And on the surfaces, I will have polarization surface charge, and it will be positive on the let's say, exit surface of the polarization, and it will be negative on the entrance source of the polarization. And by entrance, I mean that's where the vector starts. Okay, let's calculate. Oh, and by the way, since we are at it, the electrostatic potential in the origin, if you are at the very origin and the polarization is symmetric and the body is symmetric because we have placed the origin at the center of mass of a symmetric sphere, what is the potential going to be like? Can anybody tell me? In principle, what do you think the potential is going to be like at the origin? Anybody? Just guess. Null. Very well, Ignacio. Yeah, because if you sit at the origin and you look at the charges around you in all directions, you see the same contribution maybe from positive and negative charges, maybe? We'll see. The answer in principle is, if you look very close, yes, because we have all this volume charge, and this positive and negative are sort of equal. However, there is something else, and it's all the positive charge here in the top surface and all the negative charge in the bottom surface. Then, you know, positive and negative charges placed at symmetric distances, as long as the charges have the same value other than their sign, they actually create potential that are equal but have different signs. So they will probably compensate each other, and this is what's going to happen. Very likely, the potential in the middle of the sphere has to be 0. Get used to analyzing problems like this. Most times, you'll probably get to develop a physical intuition that will get you to the right answer. And then if you are in an exam working about these problems, and you get to the result that you were expecting of 0, for example, in this part of the problem, you'll be so happy and so relieved, and I'm doing things right. And actually, in an exam, it's really good to feel that you got it right? Because then you relax and keep going and succeed, right? Sometimes you will also get to the situation like it happened to me with problem 7b of last week, that your physical intuition contradicts the mathematical solution of the problem, and then you have a problem, right? So I'm thinking about problem 7b. I'll upload, by the way, a revised version of the problem, as long as I come to some middle ground between my physical intuition and the mathematical response, which is correct. But anyway, it's not important right now. The thing is, let's calculate. First of all, polarization, bound charges. The surface polarization contribution, it's going to be P times the normal vector, but then the normal vector on the surface of a sphere, it's always UR. Remember, the normal vector points outwards, right? For a sphere, this is the radial direction, so I have to do the multiplication of P times UR. Now, P goes like UZ, okay, goes in this direction, and then the radial angle, well, the radial direction goes out radially, and the angle between those two, let's call it theta. And therefore, the scalar product is module of P, that would be P 2 times 10 to the minus 6, times module of UR, that's 1, times the cosine of the relative angle. Okay, there is a cosine of theta missing here. Oh, sorry about that. Because they actually asked me for the polarization charges. And therefore, I have to give the final solution. That would be P times cosine theta. Well, okay, 2i 10 to minus 6 cosine theta coulomb per meter square, which is the units of surface densities. Okay, so that's good. Fine. Solution, end of it. And then the volume polarization charge is rho. There will be minus the divergence of P, but the derivative of the thing that is homogeneous, the just the number, is 0. So as we expected, just from our intuitive thought, the densities, the volume charge density, the volume bound charge density has to be 0. And actually, this result is general. Every single time you have a body that has an homogeneous polarization, the volume polarization charge density is going to be 0. In other words, for electrical purposes, I mean, when it comes to calculating fields or potentials or whatever, all I'm going to care about is surface charge densities. Okay? And then comes the second part of the problem. Okay? Then we'll do that in a moment. That will be the electrostatic potential and R equals 0. But then what is the aspect of my sigma, the charge density? Well, I have a cosine here. A cosine of theta, and theta is the polar angle, going from 0 for the North Pole all the way out to pi radians at the South Pole, from 0 to 180 degrees, if you want to look at it like that. This means that the cosine of theta equals 0 at the North Pole is 1. The cosine of pi is minus 1. In other words, I have a plus twice 10 to minus 6 contribution right there, and a minus 10 to minus 6 contribution right at the South Pole. And in between, I have a thing that varies like a cosine. It goes to 0 on the equator, and it just decays smoothly from positive to negative. I have a maximum positive charge at the North Pole. I have a minimum negative charge at the South Pole. In other words, if I try to, let's say, plot the surface charge densities, there are lots of positive charge at the North Pole. There are lots of negative charge at the North Pole. And the charge density decays. It means that the charges are more spaced away from each other. As I move closer to the equator, all this negative charge becomes less and less spaced, and it goes to 0 right at the equator, and then it becomes positive. So this is really like a big dipole, just like Alejandro was saying. As a matter of fact, this problem is exactly the one that you have in your homework, but just the homework is a circle, and here we have a sphere. But for the rest, it's actually a very similar way of thinking of it. Your problem, as you have already realized, is a dipole. It's a pure dipole. There is no quadruple contribution. There is no net charge contribution in your homework, right? It's just a dipole. Well, same thing here. And then when they say calculate the potential at V equals 0, like we had already thought, and Ignacio said quite rightfully, the potential that this charge distribution generates at the origin is going to be 0, because the positive potential generated by the positive charges on the top half of the surface is going to be compensated exactly, just perfectly 100% with the potential generated by the symmetric density of negative charges at the bottom half of the sphere surface. Okay, so, but let's calculate anyway. Let's just calculate the potential at r equals 0 as my definition of surface plus volume charge densities. This is the one that we had before. Well, in our particular case, I am calculating that r equals 0. First thing I need to know. Second thing I need to know, rho is 0. So there is no term here, out. And also this term r goes to 0. And what am I going to have in here? Just the modulus of r prime, right there. And what do I have on top? Sigma, this sigma, times ds prime. How do I calculate now? Well, first of all, need to have into account that r prime, the modulus of r prime on my sphere is known. Because r prime, remember, is the coordinate that tells me where my sources are. Where are the surfaces? On the surface of the sphere. What is the modulus of r prime? In other words, the location vector for any possible point on the surface of a sphere, capital R. So what I have down here, right here, this r prime becomes a capital R. Now, my equation becomes something that has an R down there. And then who is sigma? Sigma is P times cosine theta. All right, there is sigma cosine theta. And now I have my ds in spherical coordinates, just use the Jacobian, and it will be r squared, but then r again on my surface is capital R, right? Sine theta, d theta, and then there is my d phi, that will be the azimuthal angle that will go from 0 to 2 pi, and of course theta will go from 0 to pi. Now, when I do this integral, it's actually quite easy, an integral to do, because this is the sine of 2 theta, but actually you don't even need to do that change, because here is just the integral of, what is the sine? I did this one as the sine of 2 theta, I think, because this is the sine of 2 theta, so therefore it should be minus the cosine of 2 theta. So anyhow, we come to the realization one way or the other that my potential in the middle of the sphere is null, as we expected. It couldn't be otherwise, okay? The point here is that what I wanted really to say before we finish, like Alejandro was asking in the first place, the sphere actually is like a massive dipole. It really is, independently of that integral being right or no. There, what I have is some negative charge density with a center of mass, which is somewhere over here in the middle of the axis of the sphere, in the z-axis, not in the middle, but actually I think it's at the 1/3 of minus the radius. And then a positive center of mass right here, more or less, not quite at the North Pole, but a little bit beneath, that actually behaves like a dipole, right? And in fact, and if you want to look into it, I can just look at the, you can try to calculate if you want it like a dipole, or look at the Griffiths book where the whole thing appears. What you get is that the whole potential in the whole space in spherical coordinates r theta. I'm not pointing phi because there is a contribution. There's a symmetric. There is symmetry in phi right here. This can be actually seen as dipole dot r over r, the modulo of r to the square, and actually for r minus, let's say, over outside is just like a dipolar contribution, and this would be it, and inside the potential becomes like this, and the field in cylindrical coordinates, just making use of the fact that in cylindrical coordinates, r cosine theta would be z. You could actually rewrite the potential like that and come up with a realization that within the sphere, the electrostatic field is uniform in here. Okay, I'm not doing this into much detail. If you want to look at it in the Griffiths, but it's just an example of I'm just trying to answer Alejandro's previous question. This is like a big dipole, yes, and inside the dipole the field is homogeneous, and actually the potential looks like that. Okay, so yes, the sphere is like a dipole. This is what I want to come to. This is the sketch. If you plot this field that I just wrote inside and outside, and I don't really care about the actual analytical expression by itself. Like I said, look at it in the Griffiths if you want to, but I want to, for a moment, just look at the field lines. This I really want to do. Inside the sphere, the electrostatic field lines go from north to south and they are homogeneously distributed and they have a direction opposite to the polarization, and this is very important for you to remember, the field, remember this dielectric has been polarized by an external field that was pointing upwards so that we get positive charge on the top and negative charge on the bottom half of the sphere. Right? Inside the dielectric, the polarization field, the field generated by polarization charges, points the other way around. It wants to shield the external field. It just can't shield it 100% like in a conductor because there is not enough mobile charge to actually compensate all of it. There is some field inside, and in this particular case is constant, but the polarization, what we will call polarization field, or in other words, the field due to the polarization charges, is opposed to the external field because it tries to compensate. It just cannot do it 100%. The integral that yields 0. I mean, yes, Alvaro, I understood that. I will look into that integral, but like I said, let me just finish with this and I'll eventually put the version of the integral that is correct, but actually I think it's right, the way it is. The fields due to polarization charges oppose external fields. In other words, the system tries to react and compensate to some degree the external field. It just cannot compensate it completely like a conductor would because charge can move a little bit, but not completely. In other words, when an atom becomes polarized and a dipole is induced, it gets stretched. Yeah, the positive and negative centers of charge get separated from each other by a little bit. But there is also internal cohesion forces in the nucleus, in the atom, between the nucleus and the electronic cloud, that sort of say, hey, you can get away just a little bit. We cannot break the atom. In other words, charge stays localized near the atom. Slightly pulled away, yes, but not completely. So internal fields in dielectrics oppose external fields so that when we come to the point where we calculate the total electrostatic field and we add the dielectric field, this one in red, with the external one, there is a finite field inside the dielectric, but it is smaller than the external one. Okay? And then outside the dielectric, and in this particular case for the sphere is quite visible, the sphere looks like a dipole. And as a matter of fact, outside the dielectric, this particularly if I go very far away, the potential can be rewritten as the potential of a dipole with a dipole moment equal to volume, total volume of my sphere 4 pi r cube over 3, right, times the polarization. And in particular, this thing we have here is exactly the potential of such a dipole for with a module equal to 4/3 of pi r to the cube times p, yeah, for times r times over r cube. R over r cube brings me this r square contribution when I do the simplification, and then 4/3 of pi r cube bring me, and p, I mean the capital P of the polarization, give me this contribution when I do the simplification of 4 pi with the 4 pi epsilon naught of the bottom. So this is exactly the potential of a dipole with what moment? This moment. Okay? So as a matter of fact, just we can do this tomorrow, but if you want to start looking into problem number 5 of the list, is exactly the same thing, but just having a half a sphere, a dielectric hemisphere of radius r with an homogeneous polarization. In this case, they just leave it as a p0. They don't give you the result and say find the bound charge densities and the net polarization and the dipole moment created by these bound charges. This second part is actually new. The first one, the result is exactly the same than we had before. There is no net a polarization charge in the volume, and there is some surface charge on both the top half, let's say half hemisphere, half hemisphere, whatever, hemisphere is a half sphere anyway, let's call that one. And then in this case, 2 is going to be my bottom field. You can try calculating, you have the solution here. So then the top surface, we still get the same sort of contribution, p times the cosine phi. And in the circular base, since un is minus uz, then you get the contribution of to the polarization charges, which is just minus P times UZ, in other words, minus P0. Okay, no big deal. So by definition, then you can try find the dipole moment. In this case, you'll have to do an integral. We'll look at this tomorrow before we get started, but if you want to start having a look, then what you want to find is, again, that this also behaves like a dipole, just a slightly different kind of dipole. Okay? Anyhow, we'll do this tomorrow and finish the class, and I will see you tomorrow, okay? Then talk tomorrow. Bye.